Thank you very much for the invite. It's very nice to be here. I've not been to Antwerp before. It's decided to gift me with some relentlessly hot weather. I was not quite expecting this. I've not bought quite the right set of clothes. Okay, anyway, this is going to be, I'm going to talk about joint work I've been working on with Luca for quite a few years now. Some of this stuff has been out in print. Some of it is still work in progress. So I'll try and distinguish between the two. I've been told it's kind of a sort of mixed audience, so please feel free to stop me and ask questions. I can kind of stop at various places in the talk, so if we want to, I can adjust, right, as we go along. If we want to spend some more time, if I say something that sounds nonsensical, then we can chat about it. Okay. So firstly, what have I done? I stuck this equation up on the board, and hopefully I got it right. I put it up there first because I don't trust myself to be able to write it with everyone looking at me without making mistakes. So what is this thing? I mean, this is a quartic in P3, right? So I've got x, w, x, y, z are my coordinates, and I have a, b, and d. These are complex numbers. And this thing gives me a K3, well, it doesn't quite give me a K3 surface, but it gives me a quartic in P3. This thing is singular. And there is a relationship here, so A, B, and D are not sort of independent. If I scale A, B, and D by the following, lambda to the 6D, it gives the same surface. So there's an isometry which relates, and if you get lost and you're bored, try and find the isometry of this equation that relates these two things together. So actually, this forms a two-parameter family over a compact base, and the compact base is given by sort of quotienting C3 by this thing. So this thing has a couple of singularities in it. If I resolve them, that gives me a K3, and I'm going to call this K3 surface X. And generically speaking, if I look at the Picard rank of X, so the rank of the Picard group, this is generically going to be 18. So this is a K3 surface that's quite algebraic. It has a lot of divisors on it. So if you don't know much about K3s, they can be anything from sort of fully analytic, where they have no algebraic divisors on them at all, right the way through to the rank can go as high as 20. So this is quite close to being sort of the maximum possible here. If you know a bit more about K3s, so the Picard group here has got an intersection form on it, and we can identify this with a lattice, and the lattice we identify it with is this. And what is H? H is the lattice where the intersection form is given by a matrix that looks like this. It's called the hyperbolic plane. And E8 is the negative definite root lattice. Negative definite root lattice E8. So if I look at the rank here, I've got 2 and 8 and 8, that gives me 18. So this is the right thing. If you don't know much about lattice theory, what does this tell me? So this is telling me something about divisors on my surface X, right? So it's telling me something about curves and things living on my surface. So in particular, this tells me, what do I have? So pic X is generated as a Z module by classes of -2 curves. So there's a set of rational curves on X. And I'm going to draw a diagram here, and I have to stop for a second, count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. It goes on way longer than I think it's going to. Right, so there are 19 -2 curves, and this is the dual graph. So what does this mean? Each vertex corresponds to a -2 curve, and two vertices are joined if those two -2 curves intersect each other. So essentially it's equivalent to say, pic X is this, and there is a configuration of -2 curves on my K3 that looks like this. And most of these come from resolving the singularities of this thing. So a generic K3 surface just has one class, or one of these just has one class in coming from the hyperplane section. I resolve these singularities, and it gives me all this extra stuff. Now you might say, well, hang on a minute, you said it was rank 18 and there are 19 things here. This is because I want this as a Z module and it is not generated sort of directly over Z by just 18 things, or at least easily. So there is a relation between these, and the relation looks like this. 2, 4, 6, 5, 4, 3, 2, 1, 0, minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, minus 4, minus 2, and minus 3. So this is a relation between the classes of these things inside PIC, and you quotient by this relation, and you get this lattice. Okay, so these 19 classes generate the effective cone. So every effective divisor, so every linear combination of any positive linear combination of curves on this K3 surface can be written as a positive linear combination of these minus 2s. So every effective divisor on here can be written as a non-negative linear combination of these. So what am I going to do now? That's the kind of geometry of the general member of this system. Now I'm going to degenerate this. So I'm going to degenerate this. I'm going to take AB to be not 1, 1. And I'm going to take, because this gives me a special case, I'm going to take D going to 0. And what happens here, well, if I do this, you know, this thing, I get a family, this thing picks up. Last has gone to sleep. Wakey, wakey, there we go. I'm talking too slowly. So I have my K3 surface here. So this is my X. And when D goes to 0, this is going to generate to X0. And if I take the sort of the family of this thing, if I take this family and I resolve the singularities in the family, then my central fiber is going to look like this. So it's going to have two components like this. This is a blow up of P2 in 12 points, and I will call that V2. This is a blow up of P2 in 6 points, otherwise known as the Del Pezzo surface, and that I'll call V1. This double curve here has self-intersection -3 in one component, -3 or +3 in the other. What's this curve here? This curve is it's anticanonical elliptic, and I will call it E. So I've got two components, and they're glued along a smooth elliptic curve. So this is what happens when D goes to 0, and I can look at sort of where these classes go. I'll draw them as curves. 17, something like this. So a bunch of these, they will go to a configuration that looks kind of like this. And I haven't counted to check I have the right number there, but it's fine. There's slightly fewer on this side, so I haven't blown up as much. Something like this. So my configuration of curves ends up going, you know, I sort of split this diagram into two. Okay, everybody's still happy.
What happens to the middle curve?
Oh, so yes, I'm going to say that in a... Oh, I'm not going to say that in a second. I'm going to say that in a second. But essentially what happens is one of these curves is a -2 curve. So I have some sort of -2. And when I degenerate, it becomes a -1 and a -1, split either side across this double thing. So I'm coming back to that. That's going to happen. So we call such a thing, maybe I won't give the full definition, but such a degeneration to V1 union E V2. So V1 and V2 glued over E, where V1 and V2 are rational, E is canonical. We call this a Turing degeneration. Turing degeneration. Okay, fine. So now what I'm going to do, I'm now going to choose a, let's choose an ample divisor, D on X. So what do I mean I mean, I don't know how much people know about algebraic geometry, but you can think of this, I'm not picking a line bundle here, I'm picking a specific choice of divisor. And what is this? I can think of it as an effective linear combination of these 19 curves, which has positive intersection with all of them. So, you know, take some linear combination of those 19 classes, intersect, so its intersection with each one is positive. Okay, now I'm going to see what happens to D when I degenerate across. So, what can happen here? This thing over here, so on X I have 18, you know, my Picard rank is 18, right? So I've got an 18-dimensional space of curves. When I go over here, well, hang on a minute, blow up 12P2, that's got, you know, P2 has one curve class on it. I've blown up 12 times. This has got 13 curve classes on it. P2 again has got one. I've blown up 6 times, so I've got 7 there. So I have 20 curve classes over here. So when I've done this degeneration, I've picked up some curve classes. X naught has more curves than X. So what does that mean? That means that there may, I don't want to say there is, there may be curves C on X naught with negative intersection with D. And we don't really want this, right? I mean, this is something where if I sort of want to understand, well, essentially what I want to do is I really want this degeneration to be projective. And if I want this degeneration to be projective, that really means that I want there to be a sort of global ample divisor. So I've got this divisor, it's ample on the general fiber, that means intersecting against all curves is positive, but then when I take it to the central fiber, it might intersect some stuff negatively. So what I want to do is I want to modify my degeneration to get rid of these curves that are negative. Okay, so this is the following is an algorithm due to Friedman and Shepard-Barron. These are not 3 people, these are 2 people. Fun fact, Nick Shepard-Barron's father invented the ATM. Okay, so I'm not going to explain the following sentence if you don't know what it means. So we're going to first form a T of flops along -2 curves in VI with D dot C negative. I'll sort of explain on the diagram in a second, but I'm sort of going to say the words first. And then secondly, if there is a -1 curve meeting E with D dot C negative, we're going to flip it to the other component. And then what we're going to do is we're going to repeat these things 1 and 2. So after I do step 2, I might get some more -2 curves in the VIs. So I do step 1 again, and I do step 2 again, and then after that I can maybe do step 1 again. And I just repeat this over and over again. And what do I get? I end up with, it's non-trivial to show this terminates for all C living in X. Okay, so let me try and kind of explain a little bit what's going on here, because, you know, I've said some words and those words maybe don't make much sense. So what I can do is, so let's suppose I have, you know, there's some -2 curve which lives in one of V1 and V2. Then what I can do is I can do what's called an Mattia flop, and what this essentially means is it essentially means that inside the total space of degeneration, so inside like the threefold total space, I sort of take this thing and I blow it up and I get some little surface here. So I sort of have a -2. And then I take this surface and I sort of contract it in another direction. And what it does is it takes this -2 curve and gives me one that sort of faces the other way, like this way. So this is an Atiyah flop. It's basically sort of a blow-up contraction inside the thing. What's this second one? This second one is if I have my thing like this and I have a -1 curve like that, what I do is I sort of contract my -1 curve and then blow it up in the other component. So I can take this and move my -1 over there. So essentially, these are some modifications that I can do to this configuration of curves. I can either sort of, take these -2 curves and do some sort of like internal modification, or I can take these -1 curves that make this double curve and I can move them between the two components, up and down.
The fact that these birational modifications preserve the map down to your degenerating parameter is it part of the package or the?
There is some. I mean, there is a little bit of stuff here which is like, okay, really one is working with analytic degenerations here. So you're just saying, okay, you have some, and like local analytic existence of these operations is an old result due to like Kulikov, Pearson, Pinkham. The fact you can do this in a way that actually preserves projectivity and algebraicity is essentially part of this.
I'm fine with that. What makes me itchy is that it preserves a map to a curve downstairs. It preserves.
Yeah, but the point is, both of these operations only modify the central fiber.
Ah.
So they don't change anything away from central. I'm just doing a birational modification on the central fiber. So everything away from there is. So essentially, another way of thinking it is like over the punctured disk, nothing changes. So everything is just happening on X naught. Everything is just happening on X naught. Okay, so here is a little theorem. Oh, now I have to start erasing words. Here's a little theorem which is I proved a few years ago with not Luca. Oh boy, I'm really pressed hard with this chalk. It's embedded in there. I don't want to get the water out because if I get the water out, I'll get filthy. Because I don't have the practice that you have of doing this. I'll just end up looking like I've painted a ceiling.
That's part of the experience.
So this is a result by Chuck Duran, who's a long-time collaborator of mine, my PhD student Joe, and me. It came out on the archive a couple of years ago, but it was published last year. There are 11 possible Turing degenerations of a K3, whose Picard group is this rank 18 thing. So this specific K3 that I had on the start, there are 11 possible Turing degenerations you can build on this. And let's say all may be obtained by this process. So what do I mean by this process? I mean, I take this specific degeneration here, this one that I've written down, and all I do is I take different divisors D. So I pick different divisors D, I run this algorithm, and it will give me 11 different possible central fibers. Choose other D. So you pick different Ds, it gives you different things. Okay, so how can you sort of see these things? Well, roughly speaking, what do you do? 8, 10, 11, 12. I'm going to draw the specific one for the example we had here. 4, 5, 6, 7. So what you essentially do is you take this sort of configuration of -2 curves you've got here, and you sort of pick a place to split it. So all of these are still -2s, but then you have one, as I mentioned to the question earlier, where I get a -2 and it splits to a pair of -1s. So you sort of essentially choose where you're going to do that, and then everything else stays a -2. So you've got somewhere here where this sort of split comes, where you sort of fold your surface, and some of your chain of -2s go one way, and some of your chain of -2s go the other way, and in the middle you have -1, -1. And up to symmetry, you can see there's 11 ways of doing this. okay, things get more complicated around the ends because of these branches, but this is the rough idea. Okay, cool. Everybody's still happy. So, you know, I was 41 last week. And so far, nothing I have said really is younger than I. Right? Like, you know, Friedman and Shepard-Barron did this work before I was born. Okay, this theorem was a couple of years ago, but like Friedman and Shepard-Barron could have done this theorem. They just didn't care about this, right? You know, they had no reason to think about. I mean, these surfaces, this form that I wrote down at the start, this quartic for these rank 18, this is written down by Innersay in 1977. So you know, this is not a new theorem because it is hard. This is just a new theorem because nobody has asked this question before, right? Okay, now what I want to do is I want to completely switch gears and talk about mirror symmetry. So maybe I should get a new board for this.
What was Nose's goal in writing down the mechanics? Just find the.
Well, actually, Innersay was looking. He was studying singular K3. So in this, when I say singular, I mean in the sense of like you know, rank 20. So actually, he was writing down this family as a way of studying. Like there is a way you can take this family and enhance it up to rank 20. So he was actually interested in studying rank 20 K3s. He just kind of got this as a step on the way to that. But he proved some properties of this. So, you know, essentially this family's been known for a long time. But this is long before lattice polarizations came along, right? So it was kind of, okay. So if you want to know about mirror symmetry for K3s, you look at the paper from the mid-90s by Dolgachev. And what does it say? It says the mirror to a K3 with, you know, these ones we've been caring about. This family will be looked at. So the mirror to one of these is a K3 with pick isometric to H. So there's a good reason here. Like somehow, you know, I said the maximum rank that pick can have is 20. Like these two things sum to 20. This is kind of what the mirror symmetry is doing. It is exchanging a rank 18 lattice for a rank 2 lattice, and these two things sum to 20, right? So it's more complicated than that. That's the basic idea. It's sort of swapping, somehow it's swapping the algebraic and the non-algebraic classes in the second cohomology. So you've got this stuff is pick is encoding your algebraic classes, there's a bunch of non-algebraic classes, and somehow mirror symmetry is sort of swapping these two groups of things. Okay, so what is a K3 with pick isomorphic to H? So this is just an elliptically fibred K3. Let's call it pi from y to P1. It should have a section, and it should have 24 fibers of type Kodaira type I1. So again, there's a few things. So the how can we see this? Well, if I draw something K3 surface, it has a section. The section necessarily has self-intersection -2. It has a fiber which has self-intersection 0. So this generates a lattice with intersection form this. So section and fiber meet in 1 point. Fiber meets itself 0. Section meets itself -2. This is isometric to by just change of basis RH. So this is kind of how you see this. What do I mean by a fiber of type I1? These things are just nodal elliptic curves. So by which I mean one node, so these. Right, the simplest kind of singular fibers you can have. Okay, so here is the conjecture that we care about. And again, I'm going to state this in the vaguest possible way first, and then try and drill down a bit to explain what this means. So this was again Chuck Duran, Andrew Harder, and me. It was published in 17, but it hit the archive, I think, in 14. So it's more, I've been working on this more than a decade, that's not good. So what does it say? It says for any Turing degeneration of a K3, let's say V1, central fiber V1 union V2 of a K3, the mirror K3 should admit an elliptic fibration y to P1 and a splitting. So I can write P1 as, and I'll explain all of this in a second, and the splitting this such that the restriction yi to delta I, so restriction of this fibration to each of these bits looks like, in inverted commas, the mirror to vi. Okay, so I've sort of waved my hands an awful lot there, right? So this is easiest to explain with a picture, but we can kind of see, you know, like in this example, we had a Turing degeneration of this K3 I had up on the board before, this nice splitting, and then, you know, we can see the first part of this, right? The mirror K3, which is this thing, should admit elliptic fibration. Well, yes, it does. In this case, it's a generic elliptically fibered K3. So what's the kind of, you know, what I really need to do is explain what do I mean by a splitting and what do I mean by looks like. Because I've sort of waved my hands and said something very vague there. Holy moly. I need to press less hard. So carving it into the wall. Okay, so here is my P1 base of my fibration. And what do I mean by splitting? So there's some various critical points in here, right? Here are some critical points where my fibers are singular. And so the first thing I mean by splitting is I'm going to choose some simple closed curve in here, gamma, which is going to divide this thing into a pair of disks, or two things topologically equivalent to disks. So, you know, this is delta 1, this is delta 2, they're two disks. I have y1 living over there. I have y2 living over there. So I've sort of taken this elliptic fibration, I've just sort of cut it in half somehow. The following is sort of a consequence of a paper by Oru, Katsakov, and Orlov in 06, and Andrew Harder and I in 2020 in different cases. And it says if Vi is one of these components and it has anticanonical, so this is a square of the double curve essentially on that thing. So on the one I had before, this is 3 and minus 3. But if this is equal to D, its mirror should be an elliptic fibration over a disk. It should have 12 minus D singular fibers, counted with appropriate multiplicity if they happen to be worse than I1s. And moreover, the clockwise monodromy around the boundary should be 1D01. So Oru, Katsakov, and Orlov did this originally for just Del Pezzo surfaces. And for Del Pezzo surfaces, you can actually do this where rather than taking a disk, you can take the base to be the whole of A1. And what does this monodromy condition mean? It means you have a one-point compactification to a rational elliptic surface over P1 as an ID type singular fiber at infinity. So that's all kind of old. We wanted to do this for surfaces which are worse than del Petzo, so have been blown up more times. So we wanted to allow D to be negative. The problem is if you allow D to be negative, you can't do this over the affine line anymore because there's no fiber you can glue into 1 point compactify where this thing comes out to, which has an order of -1 around it. So, but you can do this if you shrink your base fluid disk. Okay. So, what would we like to do? I mean, what's kind of the aim here? The aim here is to show that, well, okay, yeah, the main aim of what I'm going to talk about today is to show that for this family that I gave you at the start, we can prove this. So the first step in this, and how are we going to do it? What we're going to do is like we did at the start. So how do we construct all of the Turing degenerations? Right, to construct all of the Turing degenerations of this K3 I gave you at the beginning, well, we constructed one special one, and then we used this algorithm of Friedman and Shepard-Barron to build the other ones by putting an ample divisor on there and then running this algorithm, right? So we're going to try and do the same thing. So the first thing we need to do is build a special one, right? We're going to build a particular example of one of these, and then we're going to so here is a proposition. We proved this a few weeks ago. It hasn't been written. Well, it's in a set of notes that are printed out in my bag, but it's not available anywhere you can read it. If you're not Luca, Luca can read it. So if pi from pi to Peter, if this is elliptically fibred K3 with pick y the hyperbolic plane, then there exists a splitting P1 into like this with 12 y1s on each side, and monodromy 1, 0, 0, 1. And, you know, I've sort of brushed a little bit under the carpet because we should, you know, somehow, I mean, I said, okay, the mirror should look like the mirror to V1, and I gave you something there. I mean, this should be a stronger statement than this. And so another thing about what these mirrors looking like is like, well, okay, what did I have in my Turing degeneration? I had these sort of 19 special classes, right? So I had these 19, these 19 curves, and somehow this splitting somehow respected these 19 curves, right? So, you know, it sort of took this diagram of 19 curves and kind of cut it in half, cut it into two pieces. So, moreover, and there exists a set of transcendental, so non-algebraic, two spheres in Y, which look as follows. How do I want to draw this? Do I have enough space here? So these are all spheres. I wonder how many coloured chalk. Is there coloured chalk there? Yeah. So, how do these things? I'm going to sort of draw I wonder what orange is like. Let's see what orange is like. So, how does this work? How do we build these things? So, firstly, how do we build this? So, firstly, the way we construct this is we take a very special K3. We take a very specific choice of one that has an involution on it. And the involution switches these two things. And so from this involution, we can quotient down to a rational surface that has exactly 12 y1s. And then lifting up this splitting, the splitting curve comes exactly from a branch cut of that double cover. So we sort of realize a special one of these is a double cover of something with only 12 y1s. Under that double cover, we take a branch cut, that gives the splitting curve, and then we deform to get this in general. So that kind of gives this construction. How do we build these transcendental two spheres? Well, there is a bunch of critical points So here are a bunch of critical points. Here are a bunch of critical points. So these are all critical points. And if you join these critical points by paths, so let's say critical points, these are paths. And what you'll get is, like, for each critical point for a singular fiber of type I1, you have a vanishing cycle. So if I take a torus, you know, what does this special fiber look like? This special fiber looks like a pinch torus. I've sort of contracted something down to a node, and what's happened here is that, like, there is some sort of loop in here, and that loop has contracted down to this point. So I get something which looks like a thimble, right? It's like, you know, you can sort of poke your finger in it. So you have some kind of vanishing cycle here, and as I deform down and we go towards this singular fiber, this thing contracts down to a point. And so what I can do is, if I choose paths judiciously between my critical points, I can get, coming out of here, I get a vanishing cycle that appears, and then when I go into the next one, it disappears again. And this gives me a sphere. So what's essentially happening here is, over this, I'm going from, there's a critical point, a vanishing cycle blows up, and it goes back down again, and I get these two spheres. So these paths are chosen carefully to allow this to happen, like so. And somewhere in here, I will get, here is my curve gamma, and somewhere my path will cross over gamma, and when it does so, you know, the pre-image of gamma upstairs will take my sphere and cut it into two pieces. So I end up with something that splits up as like a pair of thimbles. Okay, now what I want to do is I want to now I've got this special example, I want to run an analog of this algorithm by Friedman and Shepard-Barrett.
Can I ask you stuff?
Yeah, go for it.
So, any K3 with Picard H plus C8 plus C8 will be mirrored to this example, right? By definition.
I mean, generally, like mirror symmetry is something which relates a family of things to a family of things.
Yeah, but I mean, just the sentence you wrote there, like a mirror to a K3 surface with Picard blah.
Yes.
A K3 surface with Picard the complementary.
Yes. Well, I mean, sort of. The way to think of it is like a generic one on each side is somehow mirror.
Okay. So, so this will be mirrored to anything, and then this extra data that you found will tell you.
Yeah. So essentially, the K3, just the K3 with the fibration on it. This is mirror to my original X. Now, this extra data is something that we're adding on top to try and mirror this degeneration that has occurred. As we found, like in that degeneration, so essentially the way of thinking about it is like the general fiber of our degeneration. This was not changing at all, right? We had this degeneration. It was the same thing over the punctured disk. It's the same family. So that is giving us this Y to P1. This is our elliptic fibration. It's the same thing. But the idea is, like, for each of the different 11 singular fibers I can glue in there, I can pick different loops in here that split this up in a different way. That's essentially what we're trying to show.
Okay.
Does that?
Yeah, I think it's the way.
So yeah, I mean, maybe I can say like you know, we have sort of a family like this over a punctured disk, and you complete this to that, right? And in here you have x naught over 0, right? Yeah. And so this sort of bit of data here is really giving you like Y to P1. There are 11 ways to do this. There's 11 different singular fibers I can glue without changing this data. So what that should be saying is it should be saying 11 ways to split. Right, so there should be, this is a special one. We've built a very special one that somehow corresponds to a case where I have a symmetric thing here, because both these sides are equal, the monotomy is constant, it's identity. But there should really be like 11 different ways of doing this, where somehow I sort of move this curve gamma around, and it should all behave well. So previously we had this special example that I built, which is taking d to 0, And then to get these other 11 examples, I took these different ample divisors, ran this algorithm, and this built me the different central fibers. And so that's what we're going to try and do here. We've got this special example that we've built by doing, I sort of described it in words but didn't write it down, right? By doing this involution, taking a branch cut. So we've got this special example we can build here, and the idea is we want to try and do the same thing of like running this algorithm to build the different examples. Okay, so the first question here is what is the mirror? So to make these things, I needed to use an ample divisor. So the question here is, what is the mirror to an ample divisor? So again, we can look back to Loughborough. The next 5 minutes or so is going to be maybe a little bit technical. I don't know an easy way around this. Maybe you thought the last half an hour has been a bit technical. So I've got the period vector of y. What is this thing? This is the transcendental lattice of y. So what's the transcendental lattice of y? The transcendental lattice of y is the orthogonal complement of the Picard lattice inside the second cohomology. So T of y, this is pick y orthogonal complement, and it's isometric, and I'm going to write it in the following way. It's isometric to the following lattice, and I'm going to sort of bracket it like this. So somehow this is something that controls the deformations of y. It's really sort of like it controls the moduli of y. So I'm going to project this to some sigma bar in the second factor. So this factor here. I'm going to test this over R. So what is this? It's projection of the imaginary part of sigma to the H plus EA factor. So here I'm just following what Dolgochev tells me to do, right? And this is just some lattice theory. Then what do I do is I define delta plus to be the set of simple roots, delta in H plus E8 plus E8, in H plus E8 plus E8 with positive intersection against delta. So against sigma bar. So sigma bar is some class in here over R. If y is taken generically, this will be sort of very general. It won't intersect 0 with any of the integral classes in here. So I've got some class in this lattice. I mean, okay, if what I've said doesn't make any sense, maybe this is true. So, okay, I have my K3 surface y. Associated to this K3 surface y, I can build in a canonical way a class in a class in this lattice tensored over R. Okay, it comes out of moduli theory. Don't worry where it comes from. I can build a class out of this thing, right? Then what I'm going to do is I'm going to say, okay, I have this lattice, sort of lattice theory. I can take a set of simple roots in this thing. It has many sets of simple roots, but I'm going to take exactly. I can define a set of simple roots to be. So simple roots are irreducible minus 2 classes. So I can take irreducible minus 2 classes in here, which are defined by exactly this relation. So for this class sigma bar that I define completely canonically from y, I just take the classes, the irreducible minus 2 classes whose intersection with this is positive. Right? And this defines me uniquely a set of these things. So what's this sort of doing somehow? This is kind of doing the mirror to these 19 effective classes. Right, so this delta plus, this is mirror to these 19 effective classes. So there will be 19 things in here. They will have this same intersection diagram. So this stuff is the mirror to the 19 effective classes. And then, okay, well, what are ample divisors? Ample divisors are just things that hit all of these 19 classes positively. So mirror to ample is A in this H plus E8 plus E8. Remember, this lives inside the transcendental axis of Y. I've used my board badly. This lives inside the transcendental axis of Y, so these transcendental classes with positive intersection with D for all D in this set delta plot. Okay. Fiddly technical bit over. If the last 5 minutes didn't make sense, stop daydreaming and staring out the window and come back again. It doesn't really matter. All that matters is I can define a mirror to an ample class A using some process. So, choose A, such a thing. Right, so now I need to do the mirrors to these two operations. So, what do I do? So, if a two-sphere in this diagram, in this picture above, has negative intersection with A, less than 0, what do I do? Well, I've got these two spheres are defined by I'm lifting vanishing cycles over paths. So what I'm going to do is I'm going to modify my paths. And the picture is quite simple. So I have a chain of paths like this, so I kind of want another color. Let's go back to the orange, that one was fairly decent. So let's say this is the one where like A dot C is negative. Then what do I do? I just take this and I replace with the following picture. I just redraw like this. So what does this do? This essentially reverses the orientation on that central path. So when I do this with the, when I calculate now, this becomes positive. So it's somehow the same class, but I flip the orientation. So rather than, if I sort of orient all of these consistently, then you sort of go from here to here to here to here, right? So you've got consistent orientation. Doing this, it reverses the orientation, so sort of this curve gets replaced by its negative. Then the second one is 2. If A dot T is less than 0 for a thimble, T. So one of these two bits which are hit by gamma, one of these two thimbles here or here, we're going to move gamma as follows. And so what do? We have something here where I have gamma, and suppose this is gamma, and suppose here is the segment of path where like A dot T is negative. Then what do? I'm just going to take this gamma and I'm just going to move it one to the left. So now it doesn't hit that one anymore. Okay, so here is, as the Russians say, where the dog is buried. People know this idiom?
In Germany, we have that too.
Oh, okay. I learned it from Valery Alexiev, so I'm not saying uniquely, but yes. So, the claim, which I am not going to make any justification towards, is that if I do step 1 on all the 2 spheres that it intersects negatively. So I can do this on all the 2 spheres it intersects negatively. That will terminate after a finite number of steps. Then if I have any thimble where it's negative, I move it. Doing this changes the 2 spheres, right? I have a new 2 sphere coming over here that wasn't there before. So then I have to repeat step 1 again. So I run step 1 again. It moves things around. When that's sorted out, I go to step 2. If I do this sufficiently many times, this terminates. So here is the theorem. Again, this is Luca and I, but it hasn't appeared yet. This process constructs mirrors to all 11 Turing degenerations of a K3 with so all these examples of degeneration we saw before, you can construct mirrors to them all by using this process. And essentially this works by doing exactly what we did before. Choose different names. So it rearranges your collection of 2 spheres, and it moves your loop gamma around by doing this, and it can potentially do this quite a lot. But when it's done it, you end up with a situation where you've got you have something which satisfies this conjecture. Okay, what else do I want to say? I've got a couple of minutes. So maybe I will say some things in words, because maybe I'll say some things in words because I'm running towards the end of the time. So obviously this is like one very, very special example, right? I started out with this very specific K3 surface. It is, it's very specific. I mean, somehow it was engineered to work with this construction. We sort of, why did we pick this one specifically? We picked this one specifically because its mirror is exactly just a generic elliptically fibered K3. So you have a generic elliptically fibered K3, that's the easiest case you can work with. So what we want to do in general, we want to do this for the sort of the full conjecture. So the full conjecture is, if I take any K3 surface with any Picard lattice, and it has a Turing degeneration, then the mirror has an elliptic fibration on it, and I can find a splitting of that. So what's the kind of strategy here? The kind of strategy here is, let's suppose I've got some completely general Turing degeneration that looks like this, right? Some Turing degeneration of some K3s with some lattice polarization. If you want this thing to be nicely compatible with the mirror symmetry, it must be possible to further degenerate this to a special one where this thing is polarized by this big lattice H plus E, H plus E. So essentially, if you have a well-behaved Turing degeneration, where well-behaved means it's going to work nicely with mirror symmetry, the lattice that you have here, your Picard lattice, has to be a sublattice of this thing, which means you can further degenerate it. Basically degenerate, this thing has a smaller number of curves on it. And so if I degenerate it, make it singular, I can make it singular, I can resolve, I can do this, I can degenerate it down to get this thing. Then the idea is then we run through this construction here that I just talked about, and we get y over p1, let's say y of r. This one is polarized by H. And then what we want to do is take this thing and degenerate again to y over p1. So this is mirror to the general fiber of curly X. So, what's the status of this? Well, what I talked about today. Maybe I'll get some green chalk. What I talked about today is essentially this step, right? And this step is essentially done. We know how, if I've got this thing, we know how to take it through and build the mirrors to all the different degenerations of this. Okay, what about this step? So we have some results that we proved a little while ago now, back before Christmas, that essentially says that like this thing is controlled by, there is a set of combinatorial data which controls this degeneration. And so if you sort of do this degeneration and remember the combinatorial data, it lets you go back again. So there is some combinatorial data here that lets you go back and forth between this arbitrary degeneration curly x and this very special one x bar. You sort of remember this data as you go through, and you can go back. So this is done as well. So what are we currently trying to do? We're currently trying to figure out, okay, we want to do something similar here. So the real question is, like, can we take this combinatorial data that we have over here and pass it through to give us some combinatorial data about y bar, and then use that combinatorial data for y bar to reconstruct this y, which will be mirror to the x. And that would then prove the conjecture. So that's where we are. Maybe 2/3 of the way, depending on how you count. But we've done all the easy bits, right? Okay, yeah, that's all. Thank you for listening.